Okay, so before the break, we posed ourselves the problem what is the motion. Now let's immediately start with our vector notation and what are the unknowns and knowns. So x1, y1, phi1, x2, y2, and phi2 are actually our coordinates of the system, the describing coordinates. And in a work or energy or power duality, we have forces, which are of course applied at the center of mass, a force in the x direction, a force in the y direction, and torque about the center of mass. Now in our case, the loading is super simple. It's just gravity loading. So we have m1g, horizontal, 0, and no torques, and then m2g, and then 0 and 0. And then the big question is with this, what is then the motion as a function of time? This is a t. That is our quest. Now, of course, for the equations we, not this one, the equations we have is, of course, sum of the forces is mass times acceleration, and sum of the torques is mass moment of inertia times angular velocity. But those are for single rigid bodies. And we have the problem, and maybe I should add Cm for, and we have the problem here that we do have rigid bodies, but they are interconnected. There are two joints, and one is to the ground, and the other two are connected with each other. And so, how do we solve that? Constraints. Reactions. I'm just repeating the things which I hear in the audience. Constraints, reactions. Any other ideas?
Maybe decouple the two links.
Decouple, yes. And how do you decouple them?
Replace apply two forces in the coupling zone.
Yeah, I like this. Actually, you should go back in history, and I think Napoleon, he was a smart guy, right? So what was his whole strategy? Napoleon, what did he say? I don't know in French, but I know sort of in the English language. He said divide and conquer. So if we want to solve our problem, we have to divide it into separate parts, which we do understand. And I fully agree with the audience. So just dissect it in these individual rigid bodies. And how do you do that? Well, if this was let's draw the original system again. So without all the nice coordinates and so on, just the geometry. So this is the original system. And then how are we going to say by divide and conquer? Now, you can divide it in a lot of ways. I mean, by the way, this divide we always do. What is the most powerful instrument of an engineer? Scissors. Forget all your tools. The only thing you need is scissors. Because with the scissors, we are able to divide our system. So we make cuts. We have two parts. So where are we going to cut? Now, you could say, oh yeah, I cut this body in half and I cut this body in half. You could do that, I mean. And then, of course, when you do that, you have to draw the separate bodies. So you say, oh, I have this support, I have this body, and then I have this stuff going on here with the hinge. And then I have this part. And as said in the audience, so this is not so nice. Well, if you cut, you also have to introduce forces, because those forces, they kept everything together. So here we have to do a force in this direction, right? A normal force, let's call it N1. And Newton said that action and reaction, they are equal but opposite in, so this is also N1, but in the other direction. Is that enough? Nope.
Shear forces.
Shear forces. Moments. Yeah, torque, yeah. Exactly. Okay. So, and then you continue, all the unknown forces. We have a torque here, we have a shear force here. And then you do the same for the other part. Also a normal force, like here, and a shear force. And a torque in this direction, the other way around. And you label everything. Well, let's label the first one anyway, M1, and this was the D1. And you do the same for 2. Yes, does this help? The first part maybe, because there's no applied forces, and so apparently the equations are pretty simple. I have 3 equations, the sum of the forces horizontal, vertical, but it doesn't really help. So in cutting up the system, you have to be smart. And I think that is one of the biggest problems in this whole approach for multibody dynamics. You need a little bit of smartness when you divide up your system. But here it's pretty obvious. You could make all the cuts at the joint. So, well, let's copy it. Well, that's the fun. Lasso, yeah, I had lasso. Come on, copy. So instead of doing the cuts here at this one, we're not going to do that. What we're going to do is we're going to cut it at appropriate places. And appropriate places are such that we really get 2 separate rigid bodies. And the best place, I think, oops, so go back. The best place to do it here is cutting at the joints. So we cut it here and we cut it here, right? So that's where we make the cuts. So then the separate bodies look like this. We have some support here. Then we have this body number 1. Yeah. And then we have this body number 2. Now, the free body diagrams I make here will probably get a 0 grading from Heike, because I always forget to put in a length or a coordinate and so on. So I already say it in advance, they are not completely correct, because I'm lazy. But the basic idea is here, right? Okay, so we have made the cuts, and if you cut a joint, there are actually two forces in play, a horizontal and a vertical. And let's make it very simple. We need a coordinate system, x and y here. Let's say we have some horizontal force here, and they come always in pairs. I always say a joint force is never alone. So you can have applied forces, and they are seemingly alone, and I will come back to the word seemingly, but a joint force is never alone, never. Yeah. So if you have a free body diagrams with forces who are by themselves alone, then something is wrong. Vertical force VA, and the same here on the support. And then here at B, and this was called B, and this was called A. Horizontal force in B, and a vertical force in B. Now let's try and do what Heike always wants us to do, and is put all the forces in. So this is M2G, and that's the gravity, and here we have M1G. Now we're not allowed to we have to put in dimensions, length. So let's say we have to do that. L1, and here I have to put in L2, and because it's a rigid body, we need that orientation angle, of course, phi 1, and here we need phi 2. So now they're completely correct and complete. And now the fun can start, because now we have two separate rigid bodies and an anomaly, a support. Before we look at the rigid bodies, let's talk a little bit about this thing, the support. Why do I draw that? Because strictly speaking, this is not a free body. This is not a free body diagram, right? Why is it not a free body diagram? Yeah, it's not cut loose from the rest. I mean, I only made one cut, and then the rest, the world is still connected to it. So either I should write an inertial world to it, or cut it from the world and add forces and so on. But then you go on and on and on, and it's like a mirror in a mirror in a mirror, and you never stop. But I add it to show that the force is not alone. That you remember. Oh yeah, those are the forces on the support. Okay. So now we can focus on the two separate bodies, and then it's actually super simple. For body 1, you just write down your Newtonian law. So you say, well, the sum of the forces in the x is mx double dot 1. Meaning, well, in the x I have a horizontal in A, plus a horizontal in B, plus m1g, and that should be equal to m1 x double dot 1. Well, that was super simple. Oh, it's a minus, yeah. Great, thank you. So this should be minus. Oh, lasso, yeah, I have a lasso. Yeah, this should be a minus. Same for the other direction, sum of the forces in the y direction is the mass 1 times the y double dot 1, being, I have a VA, and now I know it's a minus VB. The gravity works always horizontal in our world, and that should be m1 y double dot. And then finally, Euler, the sum of the torques about the Cm is the ICM times phi double dot. Now that's a bit more complex, I guess. So which forces? We have horizontal forces, vertical forces. So let's start with the horizontal forces. So this horizontal forces, HA, has a torque about the cm, about this distance. And this distance is, of course, the projection of half the length of the bar in this vertical direction. Yeah? So the projection of this length in this direction is L over 2 times the sine of phi. So I have, I have HA times L over 2 times sine phi 1. And this is a shorthand notation because I hate to write this. Oh, I even do it shorter. I always write this, S1. Shorthand notation for the sine of phi. Yeah? Now, that's HA, and then HB, is it plus or minus? Plus, same direction for the torque. L over 2 sine 1. Sorry, again? No, what I actually am doing is I try to discover what the contribution of all the forces on the body are to the torque at the center of mass. At the center of mass. So that is the notation here. The sum of the torques at the center of mass. Yeah? Okay, you're welcome. Yeah, we need more paper. So, plus, well, let's do it below, because otherwise, and then we move this somewhere to the side. Yeah, and then we say that S1 is that, and then we delete the L. So, okay, back to this plus. So now we have to do the vertical forces, of course. Now VA and VB, they are minus, yeah? So minus VA L over 2 cosine 1 now, it's the other arm, minus VB L over 2, this should be a 2, cosine 1. And gravity, no contribution, gravity acts at the center of mass, so no torque at the center of mass. So that's I1 phi. Okay, so that is simple. Body 2, exactly the same. Sum of the forces in X is mx double dot 2 for body 2. Meaning, well, looking at body 2, don't rotate, come back to me. Yeah. Horizontal forces are HB, that's plus M2G equals M2 X double dot 2. Same for the vertical, of course. M2 Y double dot. VB, that's a plus. No gravity, should be M2 Y double dot 2. Now that's cool. So what is driving the vertical motion of the second body? The vertical joint force, period. Of course, vertical joint force is a function of all the other stuff, but simple equation, right? Then the last one, we need, still this picture a little bit. The sum of the torques at the CM, I at the CM phi double dot. Now, we can copy a lot of ideas, HB, L over 2, and again a sine 2, that's a plus, and then minus VB, L over 2, cosine 2, gravity doesn't contribute, 1, 2, 5, double 2. Okay, so now we have this whole set of equations. So we have how many equations? 6 equations. And our unknowns in the equations are, let me see, what do we what are the unknowns? We don't know. We want to calculate what all the accelerations are, right? At the center of mass, 2. And what about the joint forces? Are they known or unknown? Unknown, eh? I have no clue what they are. I have to calculate them. Okay. So, and we have this HA, VA, HB, and VB. Making the number of unknowns is 10. Now, can we solve 10 unknowns? Yes, because the angle is the initial state. Oh yeah, yes. Thank you very much. Yeah, there was an omission. Yeah. So the accelerations and forces is what we solve. Can we solve the 10 unknowns from 6 equations? Question mark. You cannot? Okay. More people who cannot? Can I see hands for those who cannot? Can I see hands for those who can? The only hand I see is my hand. I mean, if you have linear equations and you have more unknowns than equations, how many solutions are there? Infinite. There's an infinite number of solutions. So you can always solve that. No problem. Right? So we have an infinite number of solutions. Now, does that comply with nature? So if we have this system with some initial conditions and some applied forces, can we get an infinite number of sets of solutions? No. So we're missing out on something. What are we missing? Slowly. X and Y are dependent on phi. Yeah, maybe. The joint, yeah. Exactly. The joint. And because if we look at this system, the system of equations we derived until now is for this system. And this system is just two rigid bodies floating into space. But that was not our system. Our system was two rigid bodies which are interconnected at two joints and then in space with forces. So we have to bring back the joints or to add the joints. So solution is add the joints and I always draw this. This. And I call that glue. This is super important. We have to add glue because we have to glue back our system again. I mean, if you have scissors, remember here, then you also need glue. Remember from kindergarten? You thought that was stupid? It was not. You work with scissors and glue, and that is one of the most important skills you learned. Because even in multi-body dynamic systems at the university, in your master study, you need your kindergarten skills, right? So then we glue the stuff together. And the glue in this sense is, of course, not a Bison kit or some other glue, but it's the expression that the things should stick together. Now, the only stuff we know, the only variables we have are the coordinates of the center of mass. So we have to express the joints in terms of body coordinates, xi, yi, and phi I, plus, body parameters, or how do you say that, length, body geometry. So let's focus on the first joint. So here I have this support, and that is the coordinate system. The support is in the origin, that's super simple. And then here I have that one body A, and I just draw it in a random position, right? So x1, y1, phi1, and this length is L1, right? Now, this should be joined, right? Or in other words, if I calculate the position, x position of point A with respect to starting from body, the center of mass from body 1, where is the x-coordinate? Well, the x-coordinate is at, I start here at x1, and then I walk back in that direction, and you need the projection, of course, so that's minus L1 over 2, and then it's the cosine of phi 1, C1. So that should be the position of xa, and that position should be 0, right? Because then it's in the origin. So this is an equation, and we call this a constraint equation. It expresses that point A should be in the x-coordinate of the origin. And the same we can write for the x-coordinate of the y-coordinate, of course. Equation. The same we can write for the y-coordinate. When we look at body 1, then that is y1 minus L1 over 2 sine 1. And that should be in the origin. So we have a second equation. So for every cut we made, a horizontal cut or a vertical cut, we come up with an equation. So that was joint A. Now we move on to joint B. So we had body 1 here, and that is B. And then we have here body 2. And now this should be together, right? Oh, nicer arrows. Or in other words, if we calculate the position of point B starting from body 1, being x1, this is L1, right? It's L2. Plus L1 over 2 cosine 1. And if we calculate the position of B starting in the x direction, starting from body 2, that is x2 minus L2 over 2 cosine sine 2. Then actually these two should be together, the same. They should be identical, yeah? Or in other words, we say this xb1 should be xb2. Now, I always like to write everything in a null terminating way, like this minus that is 0. So maybe we say xb starting from 2 minus xb starting from 1 should be 0. So this is going to be our constraint equation, which we expand to x2 minus L2 over 2 cosine 2 minus x1 plus L1 over 2 cosine 1 is 0. So that is a constraint equation. And of course, finally, the same we can write down for the y1, for the y direction. So y of point B to minus the y of point B should be 0, or in other words, y2 minus L2 over 2 sine 2 minus this is y, not a nice y, y1, what was it, plus L1 over 2, and there was a sine. It's 0. So now we have in total 4 constraint equations. Yeah. Constraint equations plus 6 equations of motion, making 10 equations. Yeah. Slowly. What is your question? Yeah, this is not a separate equation, you mean? Yeah. I can. Well, yeah. Okay. For nicety, I will get rid of. I can. Yeah. I agree with you. That's okay. This one, deleted this one, delete this one, delete. Yeah, there should be not a box around it. You mean? Yeah. Okay. Now you're happy, right? 8 equations? No. Listen up. No. Oops. We have 1, 2, 3, 4. Right? Okay. So, are we now able to solve this? No problems? So, 10 unknowns. Oh, no pen. My ink was unknowns. And let me repeat the unknowns. X double dot was X double dot 1, Y double dot 1, Phi double dot 1, X double dot 2, Y double dot 2, Phi double dot 2. And these constraint forces being HA, oh, that's not a nice H. HA, VA, HB, and VB. So, are we now able to solve these 10 unknowns from the 10 equations? You can, I cannot. I cannot. Because those 4 equations are not in our unknowns. I mean, it's very nice that you write 2 plus 2 is 4, and that's a beautiful equation, but it's not going to help you solve it. And the same problem arises here. I write a nice kinematic equation about, oh, the x of this and the phi of that, but it's not in our unknown, so it doesn't help us solving the system. So it's all work for nothing. Right? No? Not work for nothing? What do we need? We need more work, eh? Yeah, that's life. You think you're there, but you're not. More work. Okay. Homework. So the solution is, of course, super simple. I mean, from the constraints are, as we say, on the coordinate level. They are expressions in geometry. And if we now differentiate with time, then we get on the velocities. And if we differentiate that again, we get them on the accelerations. So let's take the first equation. Remember, we had this joint here. And we had this body here, 1 and point A, and then in the x direction. Now the first constraint was something like x1 minus L1 over 2, and I'm going to write it out completely, times the cosine of phi 1 is 0. So that tells us something about the coordinates. So we differentiate now with respect to time, and what do we get? X dot 1 minus, is there a L dot 1? Because fixed is not the word I'm seeking. Huh? Yeah, rigid body, eh? So you can also do flexible multibody dynamics if you say L dot is non-zero, right? But now we do rigid, so L1 is constant. Then cosine phi, does anybody know the time derivative of a cosine? Yeah, minus sine, eh? Times phi dot 1. Okay. Is it correct? How do you know?
Plus C, plus a constant.
No, that's when you go the other way. When you go from here to there, then you do a constant. And when you go from here to there, you delete the constant. So it's actually, this is a one-way street, I always say. You can actually not back up. You can only back up if you have an encyclopedic knowledge. Because differentiating with respect to time is an algorithm, is a formula. But integrating, there's no formula for that. You only have a book of tables with primitive functions, and then you look them up and you say, oh, that looks like that. Yeah, that is then the origin. And it sounds stupid, but it's actually a deep thought. So differentiating is just algebra, integrating is table lookup. That's why it's so hard in Maple or Mathematica to give an integral and say, what is the solution? And they usually say, crunch, 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 I don't know. If you give a formula in Maple for differentiation, they say, this is the answer. Yeah, it's algebra. So integration it's a one-way street. And therefore, you maybe also will get the feeling that finding the motion from differential equations, where you need to integrate, is not so easy, probably. Yeah? But that topic will come. Okay, let's go back and focus on this constraint. So this is the constraint on the velocity level. Now, I asked, is it correct? And then you think, yeah, it's correct because I went through the correct motions. But let's see if we can find a physical interpretation. So let's draw the figure again. So we have the body here. And we can draw a horizontal arrow here and call that x dot 1, right? And we can draw an angular thing here and say phi dot 1. And if this distance is L1 over 2, then I know relative to this point, the velocity of this point is, phi dot 1 times L1 over 2, right? But the kinetic diagram is a bit mixed up, because this is a velocity relative to this center of mass. And this is an absolute velocity. So it's a horrible diagram, but if you know the story, then it sort of helps. So how do we then find the velocity of this point A? Oh, go back. A. Well, in vectorial terms, we always learn from Heike, the velocity of point A is the velocity of point 1 plus the velocity of 1 with respect to point A. And in vector notation, this is this x dot 1, and that's not which is not completely correct. And this is, of course, this phi dot 1 L1 over 2. Yeah? These are these two terms. But this is a vector notation, and these are scalars, so I have to fiddle a little bit with cosine and sine. Or in other words, we see from the diagram that the horizontal speed of point A is, of course, the horizontal speed of the center of mass, plus this phi dot 1 times L over 2, times, and we have to take a projection, and in this case it's the sine, oh yeah, I would write it out, right? The sine of phi 1. Now does that, so that is the horizontal velocity, and of course that should be 0, because that is the support. The support shouldn't move. And does this comply with our derivative here? It's totally identical, eh? So yeah, I'm happy with the answer. And of course you can continue. We're not done yet, because this is only velocity. We have to do more work. Now we have to differentiate again, or in other words, x double dot A should be 0, or in other words, there we go again, x double dot 1. Now I have to differentiate this, and I first do the phi part and then the sine part, on purpose. Sine phi 1, so I keep this constant, I differentiate this, L1 over 2, and now I do this part, plus cosine phi 1 phi dot 1 squared L1 over 2. Now this should be 0, and this is finally our constraint equation on the acceleration level. So constraint equation on the accelerations. And again, you can interpret this geometrically, right? So again, you can draw a figure. So we have this bar, the center of mass, we have this L over 2, is that time? Yep, L1 over 2. So the center of mass has a linear acceleration of x double dot 1. And the center of mass, and about the center of mass is this angular acceleration, this one. Now, what is the acceleration of A with respect to 1? Is of course something with, again, this phi double dot 1 times L1 over 2. But we also have another term, yeah. So if we draw it in the diagram, it looks like this. So these arrows are all x double dot A with respect to 1. I could give them a different color, but I'm colorblind, so that's not helping. These two arrows, these two. So this was the phi double dot L1 over 2, and this acceleration, which we call the centripetal or centrifugal, or the centri acceleration. There's so many terms for it. Centripetal, centrifugal. Oh, that's the only one? Centrifugal, it's also a good one. Centripetal is also good. There are a number of names for the same thing. Okay, and that is phi dot 1 squared L1 over 2. Here's a double. Now, I will not do it, but if you then check here the projections of all this stuff, you will see you will end up here, of course. Mind, we have this one, we have the linear term is there. Then the phi double dot is there, and it's in the plus, and we project it with a sine phi. I agree, that's this part. And then finally we have the phi dot squared L over 2. So that's omega squared r, something like that from the quiz. And then it's a cosine. Yeah, it's in a positive direction, and we need this horizontal. So clearly this is the constraint that point A should not accelerate. Yeah. That finalizes the lecture for today. do homework 1, submit it as a PDF, and I'll see you next week. Everything is online. I'm online, you are online, we are all online.